All right, so let's start. So it's a pleasure to host today Dr. Tali Treibitz from School of Marine Sciences at the University of Haifa. So Tali does a very nice work in the marine imaging lab at the university, and interestingly, she also established a spin-off company. I guess everybody here is aware of that. Sierra, it's called, right? Sierra Vision
Yeah.
does cool things. We're looking forward to hear what are you up to, please. Thank you.
Okay. So thanks everybody, and thanks Vadim for the invitation. If you don't hear me well, let me know. Everything is fine. And also I have several movies in the presentation. Hopefully they transmit well via Zoom and so on. If there is an issue, let me know while the movie is playing. Okay. Um, So I'm working on computer vision mainly underwater, but we also have a system that is working above water. But in the marine environment, I belong to the Department of Marine Technologies at the School of Marine Sciences in the University of Haifa. So I think it's the first time I'm speaking to this crowd, and I think also Morel from our department didn't give a talk yet, right? Uh, okay, so I wanted to give at the beginning a brief overview on why it's important to work on robots in the ocean and what are the specific challenges in the ocean. And then I'll talk more specifically about things that we're doing in the department. So there is a famous saying by Arthur C. Clarke. He's the famous writer. He said, "How inappropriate to call this planet Earth when it's quite clearly ocean." And this is, you'll see this quote in many talks about the ocean. Because we feel the ocean is a bit maybe sometimes neglected, but actually it covers 70% of the Earth's surface, and it contains, if you think about the volume, it contains 50 to 80% of life on Earth. And it has direct influence on our life if with in food supply, drinking water. I don't know if you know that half of the drinking water in Israel comes from desalination, so it's actually water from the sea. It means that if the sea is polluted, it pollutes our drinking water. And we have what's more known in Israel are the new gas discoveries. Uh, it also provides 50% of the oxygen we breathe. This is not only in Israel, but in the entire world. If you think about the rainforests, then that they're famous for doing the photosynthesis and providing us oxygen, but actually 50% of the photosynthesis in the world comes from microalgae that they're tiny, but they cover large surfaces in the ocean. And it's also an important source of biodiversity. There is a famous fluorescent protein, GFP, that was discovered in jellyfish. And now this is the major protein used for biomedical imaging. You see here an example. Whenever you see neuroscience or microscopic images that have glowing things in there, these are fluorescent proteins that come from the ocean. And there is a lot is still unknown about the ocean. Recently, there was a census of biodiversity. They looked for new species in the ocean. They found 1,200 new species and also concluded that 50% of the species are still unknown. And there, if you think about the topography and the geography of the bottom of the ocean, then it has very large structures, uh, long mountain ranges, high peaks, and so on that contain a lot of life that is still undiscovered. I guess there are some people here from aeronautics, so the ocean research is often compared to space research or exploration. But if you look at the budget that it's compared because of the challenging conditions. But if you look at the budget that is allocated for each area, the ocean is under budgeted a lot. Space, I don't know, is considered more romantic and exciting. So 500 individuals have been into space, but only 3 have visited the deepest part of the ocean. And we have better maps of Mars than we do of our own ocean floor. And which one is more important to our lives? Well, I think you can guess my opinion, and I'll let you also, you know, come up with your opinion. But it's not only my opinion. There is a growing understanding in the entire world that there needs to be more resources devoted into ocean research, and also that currently we are exploiting the ocean, as you saw, but we don't know a lot about it, and this leads to overexploitation and pollution. We might be destroying ecosystems that we don't even know about. So I have a question. I want to show a few platforms that are used in the ocean. I'll start with this maybe more unique one. Have you seen this picture? Does anyone have a guess of what it is? Any guesses? No. What does it look like? So this is an actually a submarine that was built and developed especially to go to the deepest part of the ocean. This is it's called the Mariana Trench. It's almost 11 kilometers in depth. And this was the second time, and this is a manned submarine, so not an autonomous vehicle. And the person who went with it to the bottom of the ocean was James Cameron, the famous director of Titanic and so on. And this was 9 years ago. And he did it mainly for bringing into attention the complexity of the ocean. And also this was a way to contribute money to development and research in the ocean. The first time a person visited this area was in this submarine. And the people who went in there these are the names, and Picard, if it sounds familiar, the name was an inspiration later for Jean-Luc Picard from the TV series. So this is the area of the pressure vessel where the people are sitting. It's round to withhold the large pressure underwater. So here they decided to design the submarine in a vertical way. Anyone has an idea why? People are shy today. So it was vertical because the idea was that, think about the distance it needs to cover. We want it to go 11 kilometers in depth, but not a lot horizontally. So it's more effective hydrodynamically to build it vertical, as it doesn't need to go horizontally so much. And here is the pressure vessel where the person is sitting. Note these watches. It's not a coincidence. This is an actual watch that was here on the arm of the submarine outside the pressure vessel. And this is an advertisement for Rolex. So they use that to show that, the watch is strong and so on. And this was gained a lot of attraction, at least in the US, and also went into a chapter of South Park. So the goal of bringing the ocean into attention was partially achieved. They made a nice movie that I wanted to show, showing the submarine going down, but also what they show, what's nice, and you'll soon see, is the animation of an illustration of how deep is the ocean. And we usually, go to the beach, don't go so far in the ocean. It's difficult to imagine that the deepest point is 11 kilometers. So they visualize it, and the many things that are out there. I leave it to run. So it's in feet. I remind you, divide by 4 meters. So at some point there is no sunlight and everything is dark. There is still some mammals. This is the depth of the Titanic, is almost 4,000 meters. But there is still a long way to go. This is my favorite part in the movie, where you see that the deepest point is deeper than the height of Mount Everest, and then we arrive to the deepest point. Okay, so I think this illustrates the difficulty of working in the ocean and why we need autonomous platforms. The environment is very hostile to humans. We can't go scuba diving as for sports is limited in 30 meters. If you're a technical diver, you can go to 100 meters, but that's more or less that. And other than that, we need platforms to conduct everything we want to do in the ocean. This is there are two main types, an ROV and AUV. This is an ROV, a remotely operated vehicle. This is a vehicle that is connected to the surface with cables, with a tether. The tether provides its energy, and also there are cameras on the ROV, and there is an operator on the ship that operates actually like, like a game, or like you operate a drone. It can control the ROV, the position, and also the cameras, the light. It can see the person, the operator can see through the cameras what's going on. And the ROVs also have operators. So actually, if you want to do something, think about doing something in the ocean underwater, for example, constructing a gas rig or something like that. So this is an example of a large ROV operating some structure underwater, and you see it has a screwdriver. Everything you want to do is through, think about the operator sitting on the boat, operating, doing everything through this ROV. Currently, these operations are hardly automated. So the operator, the human operator, has to be very experienced to control everything and to build, to perform all these operations. I wanted to show another movie of an ROV doing a scientific job. I'm leaving the volume on.
Oh my god. It's like maybe 12.
We have to be careful because we can melt things on
Yes,
our
you can.
Right. Let's get some overhangs
Wow.
here.
Wow, that's magnificent.
Awesome!
All right, guys. How was worth the wait? Yes.
Hopefully you could hear the volume of the video. Let me know if you didn't hear the people talking in the video. I now muted it. So what you see here is it's an underwater chimney that comes from the center of the earth. And look at the excitement of the scientists that come to discover it with the ROV. I'll show you another movie from the same place. And what's nice, what's interesting here, I muted the sound. This is a very hot environment. These are chimneys coming from the center of the earth. And now soon they want to measure the temperature of the area. So look at so what happens is that they have a thermometer. The operator has to take the arm of the ROV. They grab the thermometer and manually, through the operator is on the boat, stick the thermometer in the one point, and this is the effort that needs to be done to measure one point of temperature at one point of time and space. Think about how large is the ocean, and you understand this is not an efficient way, but this is currently the only way that science is conducting underwater. So when we want to, I think this is obvious in this seminar, but of course, and also other crowds, you very fastly you understand that there is a need for autonomous vehicles underwater. This is acronymed by AUV. This is an example for an AUV. They come in different sizes and with different sensors on them. So when you want to send an autonomous vehicle underwater, it has to have a large navigation suite. Think about so GPS the signal cannot go underwater. So basically, it is navigating in an environment without a GPS, and this is why there are a few sensors here that together help the navigation. There is an INS, a DVL, a Doppler velocity logger, and sometimes there are additional acoustic sensors, and together the vehicle knows its position more or less. This is still an open question and we have a researcher in the department working on that. So I want to show you how typically these AUVs are used underwater. So typically the mission is programmed ahead of time. So the vehicle goes underwater and more or less knows the route that it is supposed to cover. This is an example for acoustic sensing of the ocean. But what I wanted to see is the route. Usually there is a pre-programmed route. The vehicle is just following the program route, doing the imaging, it surfaces, and then you look at the images. Usually the vehicles don't do any autonomous decisions or mission planning while they're underwater on the go. Now, okay, and the last thing I wanted to show.
Go down.
And this is a smaller LED
Pointer away from the boat.
that was equipped with 6 GoPros on it to track sharks. So the sharks were acoustically tagged, and the AUV was looking for the acoustic signal in the ocean and looking for the sharks. These are the views that you see now. Oh, sorry, are from the sharks.
Pointer away from the boat. Hey, Rod! Hey, Rod!
You can see here the AUV is following the shark. I saw this movie many times. All over the screen. And it's actually a very good example of why you need autonomous vehicles underwater and you don't want to send divers. So you're all very quiet today. If there are questions or something, comments, I'll be happy to hear them during the talk. But on the grounds of the understanding that there is new technology that needs to be developed in order to work in the ocean, our department was established 6 years ago. This is our facility. We sit in the Cheker Yamim V'Agamim building, the Israeli Ocean and Oceanographic and Limnological Research Center in Haifa by the beach. We have a nice facility, including a test pool, and there are several researchers working on several research topics. And maybe, I don't know if you saw in the news last week, there was some of my colleagues discovered a really rare area in a depth of around 1,000 meters in Israel, using our AUV and the ROV. So maybe I'll show you just a little bit of the article. I'll share the screen.
במשך דקות ארוכות הרובוט התת-ימי צלל לתוך הים, ובעומק של למעלה מ1,000 מטרים הפנסים נדלקו. ומחושך מוחלט גילו החוקרים אור גדול. כשאתה רואה את התמונות הראשונות, מה עובר לך בראש?
זה מה שעובר. אני פשוט הייתי בהלם. אנחנו שעות בתוך הסקר וזה, אני הולך רגע לאכול, אני מסתכל על הטלוויזיה, אני רואה משהו שלא ראיתי בחיים שלי. עשרות מטרים עד מאות מטרים של בית גידול עשיר שכמוהו לא ראינו באזור הימי הישראלי בכלל.
על קרקעית הים התיכון התגלו לפתע מאות קרישים, תולעי מים ייחודיות, בקטריות ונביאות של בריכות מלח, מהן נובע גז ממעמקי כדור הארץ.
מתחילים לזוז עם הרובוט, ויש כל הזמן תחושת התרגשות והמתנה למשהו שיקרה, ואז פתאום אנחנו רואים את התמלחות האלה, וזה אתה אומר וואו. וגם במיוחד כשהגענו לאזור של הקרישים, זה משהו מדהים ולא ראינו דבר כזה בשנים של מחקר.
זה קרה לפני כחודש בשיתוף פעולה של גורמים רבים, ובהם אוניברסיטת חיפה, חקר ימים ואגמים לישראל, אוניברסיטת בן גוריון והמכון הבינלאומי לחקר הים. כל יום עבודה של הרובוט עולה 100,000 שקלים, ולכן הוא פעיל רק ימים בודדים בשנה. החוקרים ידעו שמדובר באזור עם מאפיינים גיאולוגיים ייחודיים, אך לא מעבר.
לחקור את הים העמוק זה דבר מסובך. אתה צריך בעצם טכנולוגיות שדומות לטכנולוגיות של חלל. הרובוט הזה יודע לרדת לעומק של 3,000 מטר.
3 קילומטר לתוך המים.
3 קילומטר לתוך הים.
חושך מוחלט. מה שנראה במבט ראשון כמוצדפות חומות, מתברר לאחר מכן כי אלו עשרות אלפי ביצי קרישים. המצלמה אפילו מאפשרת לראות את התזוזות בתוך הביצה. אנחנו מכירים ריכוז כזה של קרישים באיפשהו בים התיכון?
אנחנו לא מכירים ריכוז כזה.
Okay, I'll stop that. Hopefully you got interested and you can see the rest online. So this is an ROV owned by our department that can go to 3 kilometers depth. And I didn't say that. We also have an AUV that can also go to 3 kilometers depth.
So, Tali?
Yeah.
How can you burn shark eggs underwater?
How can you what?
Burn the shark eggs. Hundreds of thousands of sharks near the beach. Burn them.
No. You want to burn the eggs?
Yeah, before they get big.
No, these are deep water sharks. But what's amazing here is that it's really this thing, we were all very excited because it's in 1,000 meters depth, but it's not so far offshore Israel. And look at the amazing things that are out there and we don't know that are there. And, you know, people might want to develop gas rigs there, and what's also very interesting is that it wasn't discovered by accident. Itik Makovsky, who you saw is a geophysicist, he looked at acoustic scans, bathymetric scans of the bottom, and he identified interesting features there, and then they sent the ROV to see what's out there. So it's a really cool discovery. It was made a few weeks ago. So this is more or less in general about our activity, and hopefully you got the feeling a little bit of working in the ocean. Now, more details about what we do. So in my lab, we work on underwater computer vision algorithms, methods to enhance the visibility, recover the colors and appearance of objects. We also work on vision for autonomous vehicles, and also develop underwater imaging systems. I won't talk about this part today, but we have an underwater microscope and an underwater multispectral camera. So actually, so what's personally, what's my goal? So, and it's not only my goal, you talk with the biologists and I'm like, okay, we have underwater, we do underwater imaging. What would you want us to do? And they say, okay, we need, we need scans of the entire bottom of the ocean with high resolution of 1 millimeter. Ideally, we want 3D models like that. And, we need it for large, very large areas of the ocean. Even if it's only corals, that's already a lot of area. So the 3D model here was done by my PhD student, Matan. This was acquired by diving. And when I just started, I said, okay, there are corals also, this is a relatively shallow reef. And I said, okay, let's get an autonomous underwater vehicle, a robot. Why bother diving? And also there are corals in Eilat, there are also corals in 120 meters. And I said, okay, that's easy, let's send a robot and the robot will take the images for us. So I was naive 5 years ago. And since then, we realized it's not so easy and trying to solve some of the issues. I'll talk about the challenges in that soon. Just if you're interested in the 3D models, we have a nice collection online. And you can also, if you need the models for some modeling of environments or so on, if it's of interest, you can contact us and also look at our collection. So let's see what are the challenges. So what's keeping us for giving the biologists a nice 3D images of the entire ocean? First, the data collection is difficult. If you want to send an autonomous vehicle, there are many challenges that are unique to the underwater environment, navigation, and also obstacle avoidance. The visibility and color in optical images are really bad. Of course, once you have many images, you want to do automatic analysis. And as you saw, the ocean is large. So one vehicle is not enough. You need to build something that is scalable. And above water, now there are many drones, also mini drones. But underwater, the vehicles, and I'll show you, because of some limitations, mostly of visibility, navigation, and so on, they include several sensors, and therefore they're still large and more expensive than drones. So I want to talk about the data collection and visibility issues. We have some works on automatic analysis on 2D and 3D. I won't talk about that. And for scalability, this is for future work. So I'll concentrate on these two topics. So for research, we bought a small AUV, a small underwater robot, a smaller one that can go to 200 meters. This is in collaboration with my colleagues in the subsea engineering lab in the same department, Moel Groper and his PhD student, Evgeny, sorry. So we bought a barebone robot from a university in Spain. We integrated downward-looking stereo pair. This was done by my engineer, Aviad Avni, and also strobes, and went to image the ocean. It wasn't, wasn't so fast, but we managed to get some mosaics. This is a photographic mosaic of the seafloor and the 3D reconstruction of the bottom. Look at the resolution, so you can identify a stingray here. We also managed to capture a turtle outside our Haifa.
Ali, quick question.
Yeah.
Is it constructed given GPS data, or can it be without GPS?
Sorry, I didn't hear you well, Vadim.
So these mosaic images, do you construct them given localization is solved, like with GPS, or do you also do this in parallel, like SLAM?
This is just from photographic. So this is using SFM, the navigation and the localization. We only have the GPS when the vehicle enters the water. So from there, we have navigation with the other sensors. It's not super accurate. We have more or less the point. And you probably know Itzik Klein in our department. He's working on the navigation problems. And I'll show soon, we worked on the stability of the navigation of the vehicle underwater. So this is another example from a reef outside our institution in 20 meters depth. So it's a strip of a mosaic, it's a rocky reef and the 3D. Now to do that, as I showed you in the movie, that you pre-program the vehicle to do some lawnmower pattern. What happens with now when you're doing imaging, the vehicle has to go slowly and close to the bottom and slower to get the high resolution images. So the vehicle that we have is called a hovering AUV, a vehicle that can hover above the ground or go very slowly. But when you look at the original vehicle, the route that it conducted, if the blue here is the planned path that we asked it to do, and the orange one is the actual path that it conducted. This is because there are some currents in the ocean and so on, and the resolution here is in meters, right? Because if we want to do a high resolution mosaic, the field of view of each image is more or less a meter or meter and a half. And then for the stitching, the navigation has to be very precise. So even if the vehicle drifts half a meter aside, this is not a large error, but it can lose the overlap between the images, and then we cannot stitch the mosaic. What Morel and Evgeny did, they added the side thrusters to the vehicle and changed simulated, of course, did a dynamic modeling and simulation and changed the thruster allocation algorithm. And then with the modified vehicle, they achieve a much more accurate navigation that enables us to do these high resolution mosaics. Now on our side, we wanted to look at the problem of color underwater. So this is a typical underwater image. Hopefully, this is a Haifa crowd, so hopefully you visit the beach often, and you know that once you go underwater, even in shallow water, the visibility is bad. You cannot see more than a few meters away. The problem is that the water attenuates and scatters the light. So while the light is propagating from the object to the camera, it is attenuated. And also these phenomena depend on the wavelength. So the color of the object, it means that each color is attenuated differently. So there are color distortions in the image itself. And the change of color depends on the distance of the object, because red, for example, is attenuated faster, but the further the object is, the more red is attenuated relatively to the blue. So the color shift is not the same in the image. If you take an underwater picture and try to improve it using some, filters on the phone or something like that, these filters do global operations. And the result, maybe one part of the image will look nice, but it won't correct the entire image. So 2 years ago, we published a method that we named see-through, a method for removing water from underwater images. This was led by my then postdoc, Dr. Daria Kainak. And we showed that we can do a very accurate reconstructions of the colors in underwater images. And the goal is to reconstruct the colors as if there were no water between the object and the camera. And what we do here, the input is a single image and the distance map. So the distances of the objects in the image. We don't use this. Some of our pictures include these color cards, and people sometimes confuse to think we use the color cards in the method. We don't use them. We put them there for evaluation because otherwise, we cannot quantify our error. And the strength of the method comes from a revised image formation model. So in 2 previous papers, we analyzed what happens to the light underwater when you image it with a camera. So previous models had some assumptions that we showed that they introduced errors. We analyzed the wavelength dependence attenuation and scattering, and what happens when you image them underwater with a camera. We suggested a more accurate image formation model. And this image formation model has a few parameters that depend on the optical properties of the water. And using this image formation model, we're able to recover more accurate colors. Nice pictures of corals are always popular. So Scientific American made an article about this paper. It was accompanied by a video on YouTube. It got over 2,300,000 views in like 2 weeks or something like that. So this was exciting to show that many people are interested by the ocean. And I'll show you a few examples. I'm not going into the details of the image formation model equations and so on, but I'll be happy to talk about it later. So this is an example, a raw image and our reconstruction. And this is a more difficult scene deeper in Eilat, the Satil wreck. And this is our reconstruction. And then I showed you the 3D models earlier, so we can do, this is on the right, the original 3D model that you would capture without correction. And this is our corrected model. Now, once you have corrected models, doing an automatic analysis on them is much easier, as the optical properties of the water can change even daily in some locations or between locations. So if you want to compare appearance of corals, identify corals using color or other organisms, types of sediments, types of so on, and when the color is a Q, it's difficult to use the raw images because even if you come to the same place and image them from the same distance, they can look different just because the water is a bit more turbid today and so on. So the same objects can appear very differently in different images. And this is our motivation for the correction. Now, I said that these models were acquired by a diver. And why didn't we send the AUV to do that? So to send the AUV to acquire such images, it's not so simple. As I showed you, usually the AUVs get a pre-programmed, a very basic route, and they fly in a constant altitude above the ground, and that's all. When you want to image in a complex environment like a coral reef, an underwater canyon, and so on, you need to have a delicate obstacle avoidance, right? You don't want to send the AUV to get stuck in things. And this thing is maybe above water obvious. We almost have autonomous cars that, of course, they won't hit obstacles and people. Underwater, it's difficult because the visibility is very difficult. So it's difficult to see with a camera what's ahead of you. And then if you don't see what's ahead of you, it's difficult to avoid hitting it. So, so far, all the AUVs use mostly sonar acoustic sensors, simple pingers, or more sophisticated scanning sonars. With these, they give a resolution of a few meters, but I'll show you soon a typical sonar image. You don't get a fine resolution. So if you want to navigate in a rocky reef or in a coral reef, you want to use cameras. And this is a project we're started working on using cameras in difficult visibility conditions to avoid obstacles. So I'll show you, for this, we equipped the vehicle with a forward-looking camera. You see it here. And this is a result of, on the left, an example input image from the Mediterranean. And on the right, our result, where you can see the objects much clearer, and you can see them when you're further away from them, and then it's easier, hopefully more safer to use it for obstacle avoidance if you don't need to, be 1 meter away from the object to see it. And as Vadim said, we established a spin-off company, and now we're offering this method as a real-time software for vehicle operators. Okay, well, yeah, let's see the end of the movie. And we started trying to use this method for better navigation and obstacle avoidance underwater. It's still not easy. This is a good example to the distance dependence. If you see the divers on the right, you don't see them here. The close diver, of course, you could see it. He was close to you, but the ones that were further away, it was difficult to see them. So as I said, we started experimenting to see how far can we see underwater and how can we use it to navigate an autonomous vehicle. What you see here are the feature matching of standard SLAM algorithm on the original video, on the right on our video. And hopefully you can see that it identifies objects that are further away. So it has more points. And also it can see further away. I think here, example in this rock, and I'll play it again. Look at the rocks that are further away. It can find them before this video finds it. We're still testing the accuracy and the errors in it. Even the testing is not so easy. Achieving ground truth, there are no available data sets. We are also generating data sets that include 3D. So again, if it's of interest, please contact us. We're now generating more data that includes raw images and 3D from stereo of a moving diver or a vehicle. And we'll be happy to share that.
Tali?
Yeah.
I have a question.
Mm-hmm.
So your technique, I assume, doesn't add any new information to the image, right? It's just processing what's in there.
Yeah.
If you use, let's say, a learning-based obstacle avoidance method, then at least in theory, it should be able to achieve the same performance as using your technique, right? So why doesn't that happen?
For learning, you need a lot of data. So it's true, we are doing that in parallel. We are gathering data sets to be able to train methods. And then, I don't know, in some methods you can use the original architecture. You might need to modify it for underwater. Now, the main challenge in using all deep learning methods underwater, it's difficult to have ground truth and training data. There are some simulators, but you know what you can, there is a limit to what you can achieve with them. And this is, we're doing this in parallel because if you have a general visibility improvement method, then it's nice. It might, you can use that maybe trained. This is a method that wasn't developed for underwater. So you have a larger variety of methods that you can use. And of course, once you have enough data and you'll train it, for sure you'll have better results. But we're doing it while gathering in parallel. And our next challenge is combining sonar images with the optical images. So the acoustic imaging, waves have a much larger range underwater, but much lower visibility and resolution. The sensors themselves are also more expensive and larger and so on. So we currently have the same vehicle that you saw. We have an integrated forward-looking camera and a forward-looking sonar. And we also have a small ROV that also with a forward-looking sonar and camera, and soon this forward-looking sonar will be integrated on it. And our goal is to see how we can exchange information between these sensors to do better navigation and obstacle avoidance. So just for visualization, this is if you use a camera, this blue part is the field of view. So the camera is looking forward and you get a 2D image of what's in front of you. When you're doing a forward-looking sonar, the sonar is like an ultrasound, right? It has beams and you get the range of each beam. So if the sonar is at the same location of the camera, you get the view that you get of the image is a top view. You kind of see the scene from the top, but you don't have the vertical resolution. And depending on the sonar, this is a standard sonar. You see that you don't have, the resolution is not great. I showed you that we bought a new sonar. We're supposed to get it soon. It has a higher resolution. But so what you see here is a rocky reef. This is an unenhanced video, just to give you the impression. And you see here kind of the reflections from the reefs to the sonar. So kind of an upper view. Sorry, this is not a crash in the presentation, but in the movie. So what we want to do is to say, okay, listen, this rock is actually here in the sonar. So now we have the range from the sonar, and this can help the obstacle avoidance. On the other way around, here it's difficult to see, but in the sonar, for example, here, hey, listen, we see something from the sonar. Maybe let's try to find it in the image. Maybe if we know it's there, it will be easier to find it in the image. And okay, here you don't know the height from the sonar, you don't know the height of the obstacle. You just know it's there. You don't have the vertical resolution. So if the vehicle was going this way, to say, hey, there is an obstacle here, but let's see from the image, what is the height? Maybe we can bypass it from here. Maybe we can bypass it from the sides. And we are planning to do it. As you see, these are very difficult, different modalities. And also there is a difference in viewpoint. There are not many methods that match information between them. We are planning to do it, of course, using deep learning. This is a new project and I'm looking for a graduate student and a research assistant for it. So I'm using this platform to advertise this position. And just a last note about scalability. If you have you saw the scales of the ocean, and we have, I mean, there is one vehicle, it goes slowly, there is a limit to the area it can cover. So of course the world moves to research on swarms. And just remember, there is a lot of work on robotic swarms above water. Remember that they don't have Wi-Fi, they don't have GPS, and they don't have good communication. So they can also only have acoustic communication, which has low bandwidth. We're not working on that. I'm throwing it here if, maybe someone will be interested in that. We are working on trying to do small and cheaper vehicles that are autonomous. So this is also an ongoing project in the lab of taking kind of a small vehicle that is currently controlled manually from the surface and seeing how much autonomy you can give it just using cameras. And yeah, the visibility is bad, it's difficult to see things, but as was said here, there is still a lot of room to develop specific methods for obstacle avoidance and so on for the underwater environment. And we want to see how far we can take it just using cameras, no acoustic sensors and nothing else. And that's more or less what I had to say about the underwater research. I just wanted to mention we also have a project on looking on autonomous surface vehicle. This is led by Morel, my colleague, and Alaka is a PhD student. So if you look carefully at this jet ski outside our institution, nobody is driving it. So now it is in this movie, it is remote control, but Morel and Alaka are actually controlling all the positioning, the speed, and the balance. This is done using their algorithm. The operator just gives it right and left commands. And we're also adding a vision system for it that will enable it to also be more autonomous. Okay, so I'm on time, I see. Yeah, so this was kind of a brief overview of our activities. And if you have questions, I'll be happy to unmute the video. Be happy to answer. Yeah.
Thanks a lot for this very interesting overview. Many activities in your lab. Very impressive. Thank you a lot. Anyway, we have time for questions from the audience. Questions.
Okay, so I invite you, if something is interesting, you're welcome to visit us. It's not a long drive from the Technion. And this is my website, and you're welcome to contact me.
Right. Thank you very much, Tali.
Thank you for the invitation. Bye.
Bye, everybody. Thanks.